Hello, I'm Ron Kenett. This is a joint talk with Mark Bailey, and we're going to address the challenge of data science education in the context of lifelong learning. And we're going to leverage simulations and conceptual understanding assessments. So that's the plan. We are dealing with a serious revolution in industry, labeled Industry 4.0. In that revolution, we have three layers: the sensor technology layer, the product design and manufacturing technology options that are available now, additive manufacturing, 3D printing. And in that, analytics, statistics, data science play a decisive role. To deploy that, you need to address a need. So the company needs to have a business case. You need to identify the proper methods, you need to have the proper infrastructures, and you need to upskill your workforce. So that's what we are going to be talking about. George Box, we all know George Box's saying, all models are wrong, but some are useful, wrote a very nice paper in 1997 comparing traditional methods of teaching, where the teacher is blowing facts to the face of the student, with a new approach where the problem that are dealt with in the class are unstructured, and the teacher is a mentor. So he had that vision already in 1997. And in that context, we need to address the follow-up to his famous statement, which is for unstructured problems, given that all models are wrong, but some are useful, which ones are the useful ones? So that's what the education we're talking about aims to achieve. Conceptual understanding is at the core of that. So I'm going to give you an example of teaching the use of robotics in a lab. In that lab, there is an actual robot. There is also a virtual robot. The robot has to pick up some weight, so we need to do some experimentation so that he figures, the robot, what is the weight before he knows how to deal with that task. In that context, we are dealing with how to integrate data, how to do online monitoring. So there are several conceptual aspects that the lab is supposed to teach. Intelitech is another company providing simulators. The simulators are part of a big program related to Industry 4. So there are simulators of robots, and there are actually real robots that can be set up. So there is new technology now that is available, and teachers need to focus on leveraging this technology, and conceptual understanding is one of the focus of the new approach, the new pedagogical approach. So how do you assess conceptual understanding? Well, this is a famous professor from MIT, Ed Crowley. He compares a snow machine with a snow machine, two different things that have the same name but have complete different functions. And he focuses on the concept. So what is a concept? It's an abstraction, a generalization that allows you to bundle several alternatives into one identifiable concept. So this is a tree, and all these examples are of trees. If we have that, we can see that there are going to be trees, although there are differences. So they're going to have meaning equivalence. And then there are also going to be things that might look like trees but are not trees. These are things with surface similarity. The two snow machines that Ed Crowley was talking about, they have surface similarity because the name is the same, but they don't have meaning equivalence. So this is a framework for assessing conceptual understanding. A very famous example where you have surface similarity, it sounds the same, is little sigma and big sigma. Everybody who taught statistics knows that this is a difference that needs to be made if you don't want your students to get completely confused. So the big sigma is the same meaning as a sum. So you can have representations. These are called in the terminology of the framework Q1 and Q2s. The little sigma is different. That's a Q3 or Q4. So the meaning equivalence bundle is setting up a boundary of meaning. And this is tested with a Merlot item, meaning equivalence reusable learning object, where people are shown alternatives and are asked to tick the alternatives with similar meaning. In a paper with Marco Rees, we looked at how simulations can be used in such educational programs, and we identified a hierarchical classification scheme of simulators. There are basic simulators, there are more complex simulators. I refer you to the paper for the details and for examples. Complex systems are at level 8, at HCS class 8. So this is an example of a simple simulator. It's a quincux in software that produces a normal distribution. And there are many applets for doing that. The more complex simulators of jet engines, PenSim is a process that is mapped out with a simulator for producing penicillin. The Tennessee Eastman simulator is another famous large-scale simulator. These simulators are integrated into a curriculum roadmap. The IntelliTech roadmap I mentioned has level 1, level 2, level 3. And in the next 5 minutes, Mark is going to tell us about what JUMP is doing to use simulators to train and give access to people who want to learn about analytics and statistics. So Mark, please follow up.
Hi, this is Mark Bailey. I'm going to finish our presentation today about data science educational challenges. I'm going to talk about the JUMP training pilot study. This study was proposed by Ron and will be a joint study between him and the JUMP training team. JUMP training strives to enable our users to independently be able to use our software tools that implement advanced statistical procedures. As such, the training today is provided through a highly modularized curriculum. It's made up of courses that have to address a broad range of professions and job roles. We have to use a single set of materials that work equally well in any learning situation. This picture shows most of the current curriculum. I'm not going to go through each item, but it's simply meant to give you an idea of the richness and the modularity of our training. You can see the URL at the top of the screen if you wanted to look at this yourself, or simply visit jump.com and look under Learning. The remaining courses are specialty courses taught by adjunct teachers that work with us to complete this curriculum. So the pilot study that Ron has proposed has a number of steps involved. Together with the JUMP training team, they will select a lesson from an existing training course to be adapted using his training methods. The next step will be to identify the learning concepts within that lesson and then map them. Many of our courses currently use simple simulations, although some are higher class simulation, but there'll be probably some work needed to adapt how that simulation works with the new concept map. Also, A big step will be developing Merlot items that can be used by the instructor to assess how well the students have understood the concepts from that lesson. Currently, jump training does not use the Merlot items, so this is a very exciting new frontier for making the training more effective. The team has yet to meet and conduct this pilot study. So in lieu of that, for today's purposes, I've selected a course to illustrate how this might unfold. The course that I selected is Custom Design of Experiments. I chose this course because it already uses an approach much like the one that Ron proposed, with the exception of the Merlot items. I think it's a good example because this training is based on principles of design, not methods of design, so concepts are really important. It avoids mathematical complexity while presenting complex concepts by using simulation instead. So multiple simulations are used throughout the course. They're used extensively at various times and levels. One simulation is how a metal wire breaks depending on different factor levels. The second is entirely a black box, so the student must use the principles of design to come to understand how the black box works in order to attain desired responses. And finally, there's a simulation of a real scenario where a car door seal leaks, and the factors must be explored to determine how the leaks might be prevented or minimized. So these can be used by the instructor interactively with the class, or students will use these simulators on their own in some capstone exercises at the end of the course. So what might be the learning outcomes? Again, I'm not going to go through a lot of detail. I only want to illustrate in the context of a jump training course how this might unfold. So one example might be in custom design of experiments. What is the role of sample size, or essentially the number of runs in a design, and the power? And these are very important concepts. So they need to understand that the choice of the number of runs is going to affect the power in any hypothesis test that they perform once they have the data. They need to understand power and how it depends on the number of runs, for example. The number of runs also affects the precision of the estimates. These are related concepts, but slightly different. They need to understand how the standard errors are affected by the number of runs. Of course, the power is affected by several other important aspects, but these are usually given or isolated at the time, so they can focus on one aspect until they understand it. Now, as an example, we might identify these concepts and map them in the following way, so that the power is a chance of a significant hypothesis test when the alternative hypothesis is true. Or they can think about it as the chance of obtaining a meaningful outcome, or how reproducible conclusions may be. So this is what they would explore through simulation. Now let's talk about the Merlot items. We don't have these yet, but I can talk about how they might unfold with this pilot study in the case of this custom design of experiments course. So remember, these are meaning equivalent, reusable learning objects. They're based on 5 statements about the concept. Some are true, some are not. Remember, there's both the meaning similarity and the surface similarity that are used to come up with 5 statements to be presented, and the student must find the ones that match. So the first statement is the target statement. It should be a clear statement of the concept, and the other 4 are designed to test the student's understanding to see if they match on meaning. So I now have a series of 5 slides. I am not going to go through all 5 slides in detail. I just want you to have in the slide set some potentially useful representations that could be used to build a Merlot item for various concepts. So for example, here are 5 ways that we might represent a statement about sample size or the number of runs. Similarly, I have come up with 5 statements that might be used to evaluate their understanding about variation in the response, significance level, effect size, the desired power, and reproducibility. All of these things are related. It's a very complex subject for students who are new to this idea of power, and so this will require some fairly sophisticated Merlot items to thoroughly evaluate their understanding. Now, the initial pilot effort, I've described it a bit, is going to be a live exercise involving Ron and the JUMP training team. It will focus on a specific concept. It could be the power and sample size that I just illustrated. It could be something else, like what is the meaning of a p-value, or how do I interpret an analysis of variance? So we'll develop in the pilot a student exercise. It will involve a set of instructions for how to use a simulation and a set of guiding questions that will lead them to use the simulator in a useful way. And then finally, the Merlot items that the instructor can use to evaluate the understanding of the concepts presented in such an exercise. I would now like to take just a moment and illustrate 3 different examples. These are short demonstrations. The first one is a simulation, class 1, that the current training uses to focus on how p-values behave under the null and the alternative hypotheses. The second example is richer. It's a class 6 simulation of a car door seal that focuses on the student on how to use designed experiments to learn about an unknown system and make adjustments to achieve a desired result. The third example shows how an existing simulation, class 8, that is in the popular public domain, could be reproduced as a JUMP add-in and therefore used with JUMP in a training course. I'd now like to show you 3 examples of simulation using JUMP in some of the JUMP training courses. The first example I'm going to show you is a way to allow students to understand how a p-value comes about and how to interpret it. This is from our NOVA and regression training course. We have a JUMP journal that provides everything that they need in an organized way that matches the flow of the course topics. I'll click Initial Setup so that the simulators will be ready. Then I'll click T-ratio p-value demo. This asks me for the true values. So let's say that I hypothesize that there's a pH mean of 7. The actual process mean is 7, and the standard deviation is 1 pH. I'll leave the other simulation parameters alone. We'll take a sample size of 10 and perform a 1 sample t-test, but we'll do this 10,000 times. The data is saved in a data table, and then the results are presented using the distribution platform. And what I want you to look at right now is the 4th outline, which shows the distribution of p-values. This simulation is based on the null hypothesis. The hypothesized mean and the actual mean are the same. So the only possibility is a type 1 error, a false positive. Depending on the cutoff that one uses, if we use an alpha of 0.05, then the students can discover that they will have reject the null hypothesis 5% of the time, and so their false positive rate will be 0.05. On the other hand, let me go back to my journal for a second and start this over again. I'll click the same button, and I will hypothesize that the pH should be 7, but in fact it has shifted to 8. And what does that do to the p-value distribution? Now when I look at that fourth outline, I can see that it is no longer uniformly distributed. The p-values across these 10,000 simulated t-tests, I could see that most of the results would result in a p-value less than 0.05. And now the only possibility is a false negative or type 2 error, and that's represented by the proportion that is above the designated alpha level of 0.05. And so their type 2 error would be relatively small. And this would also be useful later when talking about power. Now I'm going to change to our custom design course. This is in the last lesson in which they work individually or as small teams to explore some problems on their own. This is for a door seal. There's a button to conveniently create or start a custom design platform. It has filled in all the response definitions, all the factor definitions. It has a default model, and now the student can proceed quickly to consider a different design strategy. How are they going to experiment? For the sake of time, I'm going to click RSM to add more terms to the model, which is something they might do. Then I'll click Make Design. The custom design algorithm is now generating many different designs, optimizing each one, and then presenting us with the overall optimum. I can now click Make Table, which has all the runs and a place for all the results. Going back to the course journal, I can now click Run Door Seal Experiment, which populates the responses so they can proceed with the analysis and interpretation. So the simulation is hidden so as not to distract them from the main lesson or their activity. Finally, in the third example, I'll close this one as well. It's provided as a jump add-in. This is a popular penicillin batch process simulator. It's been implemented as a jump add-in. So I can create a response table. This is an alternative to what I just showed you in our training course. There's a window to tell them how to use it. So I'll close this and I will begin a custom design from the DOE menu. And with this data table open, I can click the red triangle and select Load Responses. So it's used those, and now I will close without saving that data table. Going back to the add-in again, I will select Create Factor Table. Then in the custom design platform, I'll click the red triangle and select Load Factors. And now I have those definitions, so I will close this data table. I'll pick a design. So Jump is now generating, it happens to be an eye-optimal design. I'll click Make Table. And we see that there are two responses. Finally, I will use the simulator to populate those columns. So I'll select Add-ins, Pen Sim Simulator, and finally Run Simulator. So the simulation machinery in all of these cases is largely hidden from the student so as not to disrupt their flow and allow them to focus on the lessons.